a specific type of centripetal acceleration can be achieved if you have one body orbiting another. So we have to actually talk about gravitation in order to actually, fully analyze the idea of centripetal acceleration. So if you have, say, the Earth, and you have the moon is orbiting around the Earth, and if we assume it's moving in a circle, it has a constant speed. And if we assume the Earth is orbiting in a circle, the moon is orbiting in a circle in this way, then we have the only force acting on the moon would be the force of gravity that the Earth is exerting on the moon. So that gravitational force is what results in the centripetal acceleration of the moon, meaning what causes it to completely change its direction. Because if you remember, when we talked about centripetal acceleration before, a force that keeps an object moving in a circle is always directed towards the center. And it is not changing the magnitude of the speed. What it is doing is changing the direction. Since the force is not anywhere in line with the speed, it can't actually slow the speed down or speed the speed up. It can't make it move more quickly or make it move more slowly. All it can do is change its direction. If, however, they happen to be aligned in some way, then that force could change the speed, along with changing the direction. So that means that we have to talk about the actual gravitational force in the context of centripetal motion, circular motion and centripetal acceleration. So the force of gravity is equal to Newton's gravitational constant times the mass of some object times the mass of the other object involved in our gravitational interaction divided by the distance between them squared. It is important to note some specific things about the gravitational force with regard to its properties. One being that it is a conservative force. So we can talk about the delta KE and the delta PE and talking about how energy is conserved with the transfer between those two different quantities. We also know that it is only an attractive force between two objects with mass. So you don't ever actually have any kind of repulsive force due to gravity. It's only attractive. It only brings objects together. And it does depend on the mass of both objects. It depends on the distance between them squared, and that's called an inverse square law. And the magnitude of the force of one object on the other is equal to the magnitude of the force vice versa, but the direction of those two forces are different. And the other thing is that you can assume that, say for example, any object orbiting the Earth, that the center of the gravitational force is actually at the center of that object. So you need to talk about everything emanating from the very center, not from the edge. So you're talking about a distance, you're actually talking about the distance to the center of that astronomical body. Out in space, usually these radii are pretty large compared to the actual size of the object, and so this can sometimes be neglected if you're approximating. But if you're pretty close to a surface of that object, say like with a satellite orbiting the Earth, then you do have to take into account the actual full radius of the Earth and then also the altitude of your satellite. So this is the force that would then create the motion of the circular motion, that would constrain the object to move in a circle. So if Newton's second law says that the sum of the forces equals ma, that the forces acting on an object result in the object's behavior, thereby meaning its acceleration, then the only force we have involved here is the gravitational force, or g, and then we put in the mass of the Earth and the mass of the Moon, divided by the distance between them squared, is equal to m of the Moon times the Moon's acceleration. Now, if we're talking about centripetal acceleration and circular motion, then that's m Moon times the velocity of the Moon squared divided by the distance between the Moon and the Earth. So at any given point in the Moon's orbit around the Earth, we can solve for the constant speed it should have, assuming it's moving in a circular orbit. So the mass of the Moons cancel, and this r cancels one of these factors of r here, and so you end up with a velocity at any given point of g times the mass of the Earth divided by the distance between the moon and the Earth. So the velocity does not depend on the mass of the moon, it only depends on the mass of the Earth, Newton's gravitational constant, and the distance between the moon and the Earth. And that all has to do with the circular motion and the centripetal acceleration that results from the behavior, from the force that causes the behavior we're talking about. So, because of this nature, we have to talk about the potential energy that is associated with this as well. And we have to think about this not just in terms of MGH, which we've been talking about, but in terms of a generic situation that's much more general than the MGH. And what we know is that if you're infinitely far away from some object, then the potential energy it has, with regard to the object in question, is zero, because it's not really experiencing any gravitational force. The force is so diluted that there is no potential energy set up. Now, what do we know about when that object comes in and comes closer and closer? What happens to that potential energy? Now, the answer is that the potential energy decreases as it gets closer and closer. How could it decrease if it goes from zero? The potential energy itself has to be negative. So the potential energy due to gravity because of being a certain distance from an object, would be equal to minus g times the mass of the object you're talking about. Say we're talking about the Earth being our gravitational object. Then we're talking about the mass of the Earth times the mass of some object in question, divided by 1 power of the distance between them. So if you think about the fact that gravitational work is equal to negative the change in potential energy, and also remembering that the work done is equal to a force times a displacement times the cosine of the angle between those two things, then we know that this can't have the same form as the gravitational force, because that's g(m) over r squared. It's instead multiplied by 1 power of r, for how far away it is, how far in it's gone, based on that work. So that's how you end up with 1 power of r. And the negative comes about based on what we were talking about with regard to thinking about the decrease, and also thinking about how the gravitational force is working on the object and the relationship between these two things. So this would be the gravitational potential energy an object has at some distance from the center of a gravitational body. Okay? So if you're talking about delta PE for an object coming from infinity, at infinity, we say that r equals infinity here, and the potential energy is equal to 0, which we kind of made a statement of before. So that means that delta PE is going to be PE final, which is this, minus PE initial, and that's minus gm, and say we're still thinking about the Earth here, gm Earth, m object divided by r, minus 0. Now, I say Earth here, but this could be whatever object you're talking about in question. So you could have an asteroid approaching the sun, you could have a comet approaching the sun, and talking about the potential energy with respect to the sun instead of with respect to the Earth. And so this would be the mass of the sun instead of the mass of the Earth, and this m would still be the mass of the object in question, which would be the asteroid or the comet that is approaching the sun. So because of these relationships, with the potential energy for gravity, you can think about the escape speed, the speed an object has to not be gravitationally brought back down. So when the space shuttle is blasting off, well, when it was blasting off, when the program was still going, it had to reach a certain speed to actually not fall back down to the surface, but instead to enter a kind of orbit around the Earth instead of falling back down. Any satellite has to do this. Planetary bodies with moons orbiting them have moons that are experiencing this sort of similar thing, but in a different way. But an object has to actually be able to leave the surface in order to get out to some orbit and not fall back down. And you have to assume that that speed at infinity has to be 0. So assume at infinity your speed ends up being 0, so you have just enough energy to make it from the surface of your planetary body out to infinity with a speed of 0. So if you're looking at energy conservation, since gravity is a conservative force, right, then the energy before is equal to the energy after, or KEI plus PEI is equal to KEF plus PEF, and at infinity, PEF is equal to 0. And we also now say that our speed is 0 at infinity, so it has no kinetic energy. So we only have what we have initially together, which equals 0. So we have 1/2 m times whatever escape speed we're talking about squared, minus g times m of some object, which is the gravitational body that we're considering, and that will stick with Earth, times the mass of our space shuttle, divided by the distance from the space shuttle to the center of gravitation. In this case, that's going to be the distance of the surface to the center of the Earth, or therefore the Earth's radius. So solving for this, we cancel out the m's, this equals 0, like I said, for the right-hand side. We cancel out the m's, we rearrange and we solve for the escape speed, and the escape speed is equal to the square root of 2 times g times the mass of the Earth divided by the radius of the Earth. So this is the speed the space shuttle has to actually get up to in order to leave the surface of the Earth and not fall back down, but instead to be in a stable orbit, moving in a circle around the Earth. And this ends up being about 11.2 kilometers per second as you're moving around and for this situation, for the Earth.